Okay, let me do this one. There was low success on this one, so let me do it. So we got vertices 0, 0, 3, 0, and 0, 2. So that makes a triangle. Like that. That's the base. That's the bottom of it. And then these semicircles are what? Perpendicular to the y-axis. So are those horizontal or vertical? Like, are they this way or are they this way? Perpendicular to the y-axis would be like this. So if we take a typical one, so like this would be, that would be the diameter, and then it would come out at you like a disc like this. Let me try to draw it this way. So here's the triangle. Here's the y-axis, x-axis, and then perpendicular to the y-axis. So yeah, like this, and then draw it in red. It'd be something like this. So something like that. So that the one with the greatest diameter would be on the x-axis, and then as you move north up y, there'd be just like it'd end up like just a point semicircle here. So the smaller semicircles would be up here. The biggest one would be down here. Okay? How do we find this volume? What do we do first? Close? Volume. Yeah, so volume of a semicircular disk. Okay, and so that's going to be primarily, so area. So the area of the circle would be half, right? Half of pi r squared, then times. Change in y or change in x? Change in y, right? Like that. It's going to be a little thickness like that. Okay, so now what's the radius of this semicircular disk? The radius would be what? From the halfway point, say, you could think of the radius right there like that. From there to there. Halfway across the diameter, because the diameter will be all the way across, and so the radius will be half of that. So pi, 1/2 pi times, what is the radius? Is it x, y, a change in x, or a change in y? Okay, yeah, so it's actually something new, right? It's something we haven't seen before. We've seen the idea, though. All the way across that diameter, you should see as the x-coordinate. So a radius would be half of x. You see that? That's always half of x-coordinate of that line. Does that make sense? Okay, and so, but we need it in terms of y, because we got delta y. So we're really talking about this line right here. This line that joins those 2 points. We want half of the x-coordinates of the points on that line written in terms of y. So we need to know how to find the equation of a line. This should be easy. This is a 0, 2, 3, 0. So can we write the equation of that line pretty easily? Y equals? Yeah, so the rate of change or the slope would be negative 2/3. And we have the y-intercept, so let's just use that. Okay, but then we need x in terms of y. So what's that? Negative 3/2 times quantity y minus 2. So okay, so 1/2 times pi times 1/2 times, solving for x, negative 3/2 quantity y minus 2. And that's that whole thing, and another parentheses squared. So I would suspect that this is where the difficulty was, getting this semicircular disk. So it's half of a circle times delta y. So pi r squared, what is r? R is 1/2 x. And then the x part, you have to get the equation of that line, solve for x in terms of y. And then we're going to integrate from what to what? First, the big disk here at the bottom is at y equals 0. And then the last one is at 2. Okay, questions? Ask me. Well, that was pretty low success, but that's you got to have the image and the setup just right, and you really got to know what you're doing on this. But still, it's nothing extremely different than what we did. Questions before we go back to physics? Okay, so we're working on physics while I'm thinking of it. On Monday, they put me on a 272, a Calc 3 272. So if you're interested in continuing with me, it's 9 a.m. Tuesday and Thursday in the fall. 9 a.m. Tuesday, Thursday. I don't know what the SLN is. So there's probably a 75% chance that that will be finalized. They're still changing things, but there's probably, so 9 a.m. Tuesday, Thursday is what they put me on for 272. So I know some of you had 270 with me, and so maybe we can do the trifecta, right? And so, like I said, high probability that will be finalized, but it's not a guarantee. They're still changing people around, okay? They're still changing people around, but I don't see any reason why they would take me off that, okay? And this is the best course of the three. It's just awesome stuff. It's super cool. We do everything we did, then we're doing it in 3 dimensions. And that doesn't add just one dimension of ideas. It adds like multiple dimensions of ideas when you just add one more dimension and from what we call R2. So these pictures that we make, this is R2, and then when you add another dimension like this, X, Y, and Z, that's called R3, and that's where Calc 3 lives, in R3. And like I said, so just adding that one dimension opens up ideas in many directions, and so it's a lot of cool stuff. Questions? Physics, back to physics now. Any questions? Well, in fact, I never looked at, let's see. Let's see if there's just any that was particularly difficult here. The first one. Okay, so I guess so we need the derivative, which is negative cosine, right? Negative sine, I mean. So how does that play out when we have this? In the end, is it plus or minus in the end? Plus in the end, right? So that minus sign, that function gets squared, the minus goes away. Minus goes away. Okay. Is this the length of a little bit of, is this the length of a little line segment? That right there? No. What's the length of a little line segment? Someone's on it. Who's talking? You need, dx is part of the math, right? This is what equals our line segment. Without the dx, it's something else. Right? We're summing up a bunch of little hypotenuses of triangles. And that's how we started. And when we did all the math, then what we got was equal to was this. Just the square root is not the length of a tiny hypotenuse or tiny line segment. It's with the dx. We're adding up that thing times dx. Okay. All right. Any questions on that? So back to physics. All right, so let's just, at the last time we talked about this. This is what we took notes on. So just remind you kind of the big takeaway from this. First of all, weight is a type of force. Weight is a type of force. Kilograms is not weight. Kilograms is mass, okay? If you need the weight in the metric units, and you're given kilograms, you need to use mg. mg then gives you weight force, and that's in newtons, okay? So weight in the metric system is newtons. If you're given kilograms and you need weight, you need to multiply by 9.8. In the English system, we don't operate in mass. We always just operate in force units, pounds. So you'll just always just start, whether it's weight or force, will always be in pounds in English units. There's not this elementary step of going from mass to force in English units. Mass in English units, the unit is slugs. It's like obsolete. It's not really used, okay? Just always operate in pounds and bypass mass, okay? So that's the big takeaway from this introductory stuff. So let's talk about, we said this, right? So, and then we also said this, that if we want to get the total work, when force is changing, right? Force is continually changing in a situation, because work is force times distance, right? Work is force times distance. But oftentimes we have a varying force as we're going, as we're transpiring through this distance. We often have a varying force as that happens. So we can't just do a straightforward calculation because the force is varying. That's when we have our concept of integral, right? Just like we've seen over and over again so far in this course. If you want to get the total work then what we need to do is we need to calculate a little typical bit of work. Okay? Meaning we're going to take a small enough distance that we can assume that the force is essentially constant. And then we can calculate. We do force times distance, right? So we're going to go over a small enough distance among the whole distance that force is essentially constant, and then we can actually do a calculation force times distance. Then we'll add them all up, right? Then we'll add them all up. Okay, so springs. Let's talk about springs as one example of where you have to do work. To push, to compress, or to stretch a spring, it takes work. It takes work because you pull it over a distance. And then what happens to the resistance force as you start pulling? Yeah, the more you stretch a spring, the more force it takes to keep stretching it. So this is a perfect example of what I'm talking about. So you're stretching it through a distance. That force is continually increasing. So how would you get the total amount of work to stretch a spring? Okay, so this F, this is the force to hold it. Just hold it still at some displacement, which is x. Okay, K is the spring constant, and x is that displacement from the natural length. Okay, so that this definitely needs to be noted here. So I've got a spring here. So we could call this right here, this natural length. So then, so this is the natural length. So x is how much you stretch it from that. It's not the new length of the whole spring. So if I stretch this thing, this, okay, so what is x? X is not the new length of the spring. This x is this dimension right here. From the natural length, this is our x, displacement. That's important, or else you get these problems wrong. Okay. The spring constant then is basically the value that gives you the stiffness of the spring. So like a slinky would have like virtually a 0 spring constant. It takes like no force to open those things up. A shock on your car wheel, would have a very, very high spring constant. You couldn't move it with your own hands, right? It takes the force of the car on the road bumping to actually make that thing compress or stretch. Okay, so that number is a number of the stiffness or the difficulty of stretching it that you have. It's really easy. A spring that's really loose and easy has a very low spring constant, and then if it's very, very tight spring, hard to move, have a high spring constant. Okay, so example. A force of 40 newtons is required to hold a spring that's been stretched from its natural length of 10 to 15 centimeters. How much work is done in stretching the spring from 15 to 18 centimeters? Okay, so what is going to be our general thing here? So we're going to be stretching this thing from 15 to 18 centimeters. And like we said before, we're going to need to calculate a typical amount of work. As we do that stretching, the force is continually increasing. So we can't just do one easy calculation of force times distance. We have to have some situation of a little bit of a constant force and distance. And so that's only over a very small distance that we can do that. So eventually here we're going to have what? A little bit of work, right? A typical little bit of work. And how will we calculate that typical little bit of work? It's still an amount of work. So how do we calculate work? Force times distance, right? So it's going to be force. But then in order to have a constant force, what kind of distance do we need? The whole point is when we're stretching this, the force is changing. So how can we assume a constant force? So we only can assume a constant force for a very, very small change in x, right? That should make sense. So like if we just move it a little bit somewhere along the way, then we could say, all right, it's essentially constant, the force, and then go from there. So a little bit of displacement is a little bit of x. Okay, so what is our force? Force, so the force, so basically, so for a little change, if you can think about we're just holding the spring, right? We're just holding it. We're barely moving it, so it's like the force to hold it still. That's what we said. That is the force to hold it at displacement x. So what is the force to hold the spring? All right. Kx, right? The force to hold it is Kx. So what do we need here? Yeah, we need K, right? So K is a constant. K is not going to change about the spring. So the distance that we've displaced it is changing, and then a little bit more displacement is delta x. So to get this typical amount of work, we need what is K? So how can we find K? So we need to look at the information in the problem to figure out what K is. And it says a force of 40 newtons is required to hold a spring that's been stretched from its natural length of 10 to 15 centimeters. That's the information we can use to get K. So if it's stretched, the force is 40 newtons equals K times what? So yeah, so we could change it to meters, or we could just do the whole thing in centimeters. We could find our amount of work in Newton centimeters or Newton meters. Doesn't matter. So let's go ahead and just change it to meters. But either way is fine. So the displacement is not 15, but what, 5 centimeters. So the value of x here from this is 5. So in meters, we've displaced it 0.05 meters. And so what is K? Is it 800? Or 8,000? 800? And that's in newtons per meter. Now, maybe this isn't the way to go, because we're talking about stretching the spring in amounts of centimeters, right? Not in amounts of meters. So maybe it makes more sense to have our spring constant in per centimeter. So what would that be? It'd just be 8, right? It'd be 40 equals K times 5. So we'll go with that. Okay, so now we've got our 8 newtons per centimeter, and we got a typical amount of work. And so then, to get the total work, stretching it from 15 to 18. So integral from 15 to 18. Is that right? Someone said something else. 5 to 8. Which is it? 15 to 18 or 5 to 8? So what are values of x, right? So these bounds of integration are values of x. And what does x stand for? Displacement. Displacement. So when it's stretched 15 long, what is the displacement? It's 5, right? It's 5. So we need it from 5, and then the displacement at 18 is 8. So these are values of x. That your bounds of integration are values of x. So you need displacement. So it's a displacement of 5 to a displacement of 8. And then this is what? A little bit of work. So when the displacement is x, this is the little bit of work you have to do to stretch it a little bit further. And we're going to add all those up as x goes from 5 to 8. So 64 times 4. 5, 6, what is that? 256? That's 100. Did I do the math right? $156, what? Newton centimeters. If we wanted joules here, so then we could change this to meters, which would be 1.56. Meters. And Newton meters, so this Newton meters, the unit for Newton meters is also joules. So joules is the unit that means as energy or work. So it's newtons times meters is the same as joules. So 1.56 Newton meters or 156 Newton centimeters. Okay, questions on this example? So easy example, but again, we're emphasizing the idea of set up a little bit of whatever you're trying to find the total of. Integration means adding up all those typical little bits, in this case of work. Yes, please. 5 to 8? Because what are values of x? What does x stand for? What is the meaning of our variable x? No, it's not distance. That's the thing. It's not distance, right? What is it? It's displacement, right? X is the displacement from the natural length, right? So it's this, how much we pulled it. So everything in this integral has to do with x, right? Since it's dx, these bounds of integration are values of x. So when it's 15, when it's at 15, 15 is not x, right? What is x then? Because the natural length is 10, and the length is 15, then that value of x, the displacement is 5. There's no light bulbs coming on. Oh, yeah, yes, there is? You got it now, okay. And so then 18, likewise, when the length is 18, you've stretched it 8, and that's what we need. That's the value of x. Other questions? Okay, so let's talk about a different kind of problem that involves work, and this is hoisting things up. So here's a 20-kilogram chain hangs 30 meters from the roof over the side of a tall building. How much work is required to pull the entire chain up to the roof? How much work? So, can't we just do force times distance? Can't we just find the weight force, the weight of this chain, and multiply it by 30? So the question is, why not? Why? So here's our building. This is a tall building. This is like, yeah, tall. Okay. 30 meters is like, oh, it's not that far. It's like, could be 10 or 12 stories. Okay, it's not that. All right. So anyway, so we've got this chain, and it's hanging down. $30 meters. Okay, so this is 30. And we got to pull that whole thing up to the roof. So my proposal is we'll find the weight of that chain, which is the force to lift it. Yeah, so the weight of something is the force to lift it, okay? So we'll find the weight, which is the force to lift it, and then we'll multiply by 30 meters, and that'll be the work. And why is that not correct? Is that too much work or not enough work? Oh, I got one of each. Too much work or not enough work just to take the force, the weight of that chain, and move it 30 meters? Or lift it up 30 meters? Too much or not enough? Too much, because as soon as you start lifting this onto the roof, what happens? You have less mass to have to pull up, right? And so it's going to weigh less, right? It's going to weigh less. The force is going to continually decrease as the chain is accumulating. The weight of the chain is accumulating on the top of the roof. The weight that you have to pull up is continually decreasing. So it's our same situation again. Okay, so what we're going to do is we're going to call, so really, let me erase some of this here. So the whole weight is 30, but we really want a typical situation somewhere in the middle. So the whole thing is 30. And so this picture I'm showing now has some chain on the roof. Okay, and so we're going to call the amount of chain still left to go x, like this. So x is how much chain is left, and we're going to call it x equals 0, the top, and then positive x pointing downward. It just seems to be what works consistently in problems like this. Okay, so why? Because we want a typical amount of work, and so we're going to freeze the situation here somewhere in the middle, and say now what's the typical amount of work right now? Okay, how do we calculate work? Still force times distance, but what distance are we talking about? 30? What's that? Nope. Because we need an amount of work to calculate work as force times distance. We have to have a constant force. We have to have a constant force. So what distance do we pull it that we can say it's a constant force? Still delta x, right? If it's any significant amount of distance, then that force is changing. So we can't calculate the work just with F, just force times distance. So it's this little bit of distance that we need to have so that we can assume force is essentially constant. Right? And so, right, Calc 1 folks, right? Calc 1 folks, this is that whole thing that we hammered the whole first week of the course, right? dy equals mdx. And then we had a changing rate function, right? A changing rate function, and we said we need to, if we pick a small enough value of change in x, then we can assume that rate is essentially constant. So it's the same thing. Okay, so what's the force now to move it? So in this particular situation, we want to move it a little bit. What force are we talking about? Yeah, so the force is the weight of the chain that still remains, right? So in terms of lifting things and holding things up, weight and force are so the force to lift something a little bit or to hold it up is its weight. So we need the current weight of the chain hanging over. All right, times delta x. So what is that? What is the weight of the chain still hanging over? Mass times, right, mass times g, mg. And the g is 9.8, but what's the mass? What's the mass of the amount of chain hanging over? Mass is changing according to x, right? So what do we know? We know it's 20 kilograms for 30 meters. Right, so we got to come up with how many kilograms for x meters, right? So if it's 20 kilograms for 30 meters, then how many kilograms is it for any number of meters? So that's just finding the rate, right? So we want, what's the kilograms per meter? So what's the rate of change for this, for the spring in kilograms per meter? How many kilograms per meter? Yeah, so if it's 20 for 30, then it's going to be 2/3 for 1 meter. So 20 kilograms per 30 meters is going to give us 2/3 kilograms per meter. And what do we want? We want the mass of x meters, right? We want the mass of x meters hanging down there. That's what I've underlined there. So we've got 2/3 kilograms per meter, x meters of it. How many kilograms is that? 2/3 times? Just so, yeah, if we have x meters, it says that every meter is 2/3 kilograms, so that every any number of meters, that would be 2/3 times that number of meters, right? Okay, so that's our typical little bit amount of work. Now there's something a little bit tricky with this. If we really want to think of this consistently when we set up this integral. So the total work to raise that chain up is going to be integral from what to what? So x starts at what and ends at what? Yeah, so let's, but look how we've defined x, right? Is it negative 30? Starts at positive 30. This is positive going down. So x is going to start at positive 30, and in the end, x is going to be 0. But now we have to consider which direction is our change in x here? Which direction is our change in x? Yeah, our changes in x are actually negative changes because positive is down and this thing is moving up. So really, when we do a little change, we're really doing an opposite. So that, like that little change right there, would be like the opposite of delta x. Because it's the direction is opposite of what we called positive x. So therefore, what do we have? We're going to have our little bit of work is going to be 2/3 x times 9.8 times negative dx. So you could do 0 to 30 and just make the whole thing positive, but it doesn't really maintain consistency with the way that we think about the problem. This maintains consistency, right? So we're thinking about it starts at 30 and we're integrating up to x equals 0. And then we say, okay, but those changes in every little change in x is really in the opposite direction of positive x. So we're going to have negative dx. Okay, and this is, that's newtons, meters, so this is going to be, easy, it's going to be something newton meters. Super easy integral, right? And we should get a positive value. So the work will be positive. The work that we have to do is going to be a positive amount. Questions on this example? Ask me if I lost you. Okay, so let's add a dimension of difficulty here. So now let's suppose we still have the 20 kilogram chain and it's 30 meters from the roof, but the chain has a bucket and it's holding sand, and that sand is spilling out as we raise up the bucket. So the initial mass of the bucket and the sand is 25, and when the bucket reaches the top of the roof, the total mass is 5 kilograms. How much work is required to pull the bucket up to the roof? So a little more complicated, more things to consider here. All right, so again, we're going to have our chain. So we'll look at it when some of it's up there. So we're just going to look at a typical situation along the way. Okay, and so we'll call that x again. We'll call this x. So what's going on with this? So what we want to do here is we want to look at what is the mass at any particular value of x. So we can start looking at some ones that we know, right? So let's make a little kind of table here. So what particular correspondence values do we have for x and m? The initial mass of the bucket and the sand is 25 kilograms, right? And so what does that correspond to with x? 30, right? So when x is 30, what's the mass of this? What's going on? So the mass is 25 But no, this is at 30, right? At 30. 25 plus 20, right? So you got all the mass. So when it's x is 30, you got the mass of the entire chain plus the bucket in the sand. And what else do we know? At 0, the total is 5. So this is 45. So then what is the mass at any, so here we are at any x value, we need to know what the mass is at any x value. What is that, how are we going to get that, or what is that a matter of? We have at 0, we have ordered pairs here, right? 0, 5, and 30, 45. Can you finish it? See if you can make any progress finishing this problem. Okay, that's the setup. See if you can make some progress finishing this. Okay, so what's really going on here is that the mass changes with x. We saw that in the last problem, and so this is nothing different. The mass changes with x. And so what is this all about here? So we've got all this information here. We need m at any length x hanging over the building, right? So we need the mass for any when x meters of chain hang over the building. So what's that all about? This is a huge part of these physics problems, is a situation like this. What is that? What are we doing? Finding what? Okay, it has to do with the changes. But in the end, so what we're going to find here is really about finding what kind of thing? That's only part of it. The rate of change it's part of it. right? This is a linear relationship. Tons of these physics problems have this idea where some quantity is changing with x, and then you've got information that's going to allow you to get that relationship, m as a function of x, and oftentimes, not always, but oftentimes that's a linear relationship. So this comes up in these physics problems all the time. So you have to have some way. Is that enough stars? Nah. One more. Okay, so yeah, so these physics problems are often about this. And so you have to have some way. Look, we have 2 points, right? We have 0, 5 and 30, 45. We're in Calc 2. And so finding m as a function of x, or the relationship of m and x, m in terms of x, is, you got to have some way to do that. You got to have some way to do that. So people will talk about the rate of change. Good. What's the rate of change of m with respect to x? So the rate of change is 40 over 30, right? 4/3. 4/3 kilograms per meter. Is it right? Is that right? Yeah, so this is just the rate of change, right? The rate of change of how the kilograms change per meter. And then, so now we need what is m in terms of x. So we can say the rate of change times x. And we're lucky enough here again to have, this is like the y-intercept, right? When x equals 0, it's 5. So it's be 4/3 x plus 5. So that is our mass at any length x for 4/3 x plus 5 times 9.8. And now we're ready to write down the work integral. Integral from, we do 30 to 0 again. And then changes are little negative changes.